Thank you, Mr. Chairman, Mr. Tröster. Yes, hello, ladies and gentlemen. My name is Niels Schäfer, and I would like to welcome you to my presentation on grid code compliance testing of renewables, new requirements, and testing experiences. I'm from Fraunhofer IWIS, which is based in Kassel, in the center of Germany. So here you see an outline of my presentation. I would like to start with an introduction, telling you about trends in photovoltaic installations and inverter technology. Then I would like to talk about grid connection of renewables, giving you an overview of the application process in Germany. And this comprises unit and plant certification, as discussed before. And I would like to consider the new grid code requirements in India. Then, as the third main point, I would like to tell you about grid code compliance testing. So what is essential to grid code compliance testing, and discuss two examples of compliance testing. Then I would like to give you some main ideas of testing infrastructure, and would like to finish with telling you about specific challenges and when testing utility-scale PV inverters. So here's my introduction slide about trends in photovoltaic installations and inverter technology. So let's start with the diagram on the right side. So as you can see, this is the evolution of PV installations worldwide, differing for the different regions worldwide. So brown at the bottom is Europe. You can see that there has been a high rise until maybe 2011, 2012. But then the Asia-Pacific region took over. And so in this region, including India, the highest rates of additionally installed PV capacity can be seen at the moment. So large PV plants, the average costs for large PV plants are at 8 euro cents per kilowatt hour in Germany, and it's much more affordable in India with 4.5 euro cents per kilowatt hour. And as discussed in the last days, India's PV target by 2022 is 100 gigawatt, with 60% installed at the utility level. So utility level usually is the installations are done by central inverters. So inverters of big power size, maybe above 500 kilowatt per inverter. So, and this share of 60% goes very well with the worldwide market share of central inverters, which was 54% in 2016. So for inverter technology, I can say that the inverters go to higher power ratings. So ratings above 2 megawatt are common in these days. And also the DC voltages go above 1 kilovolt. So as you can see here in this slide, it may appear a bit difficult, but so it's an application process for interconnection in Germany. The main point is that it is based on a certification. So DER, as used in the green boxes, DER stands for distributed energy resource. It can be one PV inverter or one wind turbine, and in one plant, so in one PV park or one wind farm, you may have more units of this. And for all different type of inverter or wind turbine, a separate unit certificate is necessary. If you have different types of inverters or wind turbine, you may have more than just one unit certificate. So, and taking these unit certificates, you also consider lines and transformers of your park, and altogether the plant is set up. And in the end, you have to So a plant certificate is set up by this. So so in the bottom there's explained the process, how approval for grid connection is done. I don't want to go into details here. Maybe you can see this reading the paper. So it just describes what data to deliver to the utility and then how the process goes on. So this is on unit certification. So the main thing is unit certification. So it is needed for, like said before, like for a PV inverter or a wind turbine. For each type of inverter or wind turbine, a unit certificate is needed. So this includes a type test. So the red boxes refer to the manufacturer. So these are the tasks of the manufacturer. In blue, you see a certification body which supervises the certification process. It's independent. So, and the green boxes represent the tasks to be done by a testing institute. So measurements for a PV inverter or a wind turbine. So this is a type test. So, and so manufacturer has to supply data to the certification body and also supply one unit to be type tested to the testing institute. And based on the measurement results, it is approved if the tested unit complies with the grid code or not. And in addition, a model is prepared, a model of the PV inverter or the wind turbine, which is then checked against the measurement, compared with that, and the certification body has to say if it is okay or not in the end. So now I come to the draft second amendment of the Indian Grid Code. So it was published in November 2016. The major changes and new requirements are, so now you also have undervoltage right-through capabilities for the solar power, and overvoltage right-through requirements are also introduced for both wind and solar. And you also introduce frequency response over voltage right-through, as said before, and voltage control and short circuit ratio SCR. So, and also is specified ramp rate when returning back to the active power. And also you have changed the capabilities for reactive power and for the harmonic emission levels. So now I come to a major point of my presentation. So I would like to discuss with you what is really essential to compliance test procedures. So it's important to define clearly a test setup. So it differs if it's a field measurement or if the test is done in a test lab. And you have to define the measurement quantities and then how the measurement system shall be laid out and how the measurement conditions are. So the sampling rates and the measurement uncertainties you have to specify clearly. And then the method of testing and the test plan has to be defined. This comprises operating conditions of the equipment under test, some the necessary set point values which are given to the equipment under test, and you have to define test sequences and also how often the tests have to be performed, under which different conditions. So, and then it's also very important to define clearly the evaluation process. So how the measurement data is evaluated in the end and what tolerances shall be taken into account. And yeah, so tolerances, I mean tolerances for the how close you come to set points and the time it takes to arrive set points. So, and in the end, you also have to make sure that in the test report everything is included. And all this leads to comparability and reproducibility of the tests. Otherwise, you cannot have a meaningful output of the tests. So as an example, I would like to talk about fault right through. So fault right through is divided into under voltage right through, also known as LVRT, and over voltage right through. Over voltage right through is a quite new requirement. And on the right side, you can see different international requirements. There are more, of course. And these are just requirements taken from Italy, South Africa, and Germany. Germany has also now introduced high voltage right-through requirements, but in these graphs only requirements for medium voltage level are shown. For medium voltage level in Germany, the requirements for over voltage right-through are only a draft version at the moment. So for under voltage right-through in Germany, this is FGW-TR3. For these tests, 5 different voltage steps are necessary. So we test at 0 to 5%, 25%, 50%, 75%, at 90 to 100%. And these tests differ in their lengths. 3-phase faults and 2-phase faults have to be done. And we evaluate in the end the build-up time and the settling time. So the build-up time is defined as when the reactive power, the reactive current, which has to be supplied, first reaches the tolerance band, and the settling time is the time when it last leaves the tolerance band. So, and also a requirement is defined for the time after the fault. So active and reactive power have to be have to return to the pre-fault values within 5 seconds. In other countries like Italy, this time is much lower. I think in Italy it's 500 milliseconds. So requirements really differ. For interface protection, for over-under voltage protection and over-under frequency protection, there also are tests to be done. For this protection, it considers the disconnection function of the inverter or the wind turbine. So here, the tests have to be performed for the threshold value and also for the release time. So separate tests have to be done, always for the full setting range. So the maximum, minimum values of the threshold and the times which can be set into the protection relay have to be tested. And the tests have to be done for over-under voltage separately for each measured voltage. This can be phase-to-phase voltages or phase-to-neutral voltages, depending on the type of the equipment. And for frequency, only symmetrical tests have to be done. Frequency normally does not vary from phase to phase. So, and in addition, at last, also a test of the disengaging ratio have to be performed for the voltage protection. Now I would like to shortly describe some main features of test infrastructure. So test infrastructure, this concerns testing in a laboratory, so not the field testing. This can be done, for example, for photovoltaic inverters. So in the middle of this block diagram, you can see the equipment under test. And in blue, we have measurement system and control system. Orange boxes are low, medium voltage test bus bar and the grid emulation. So the grid emulation on the right side, it may comprise electronic network simulator, fault right through test equipment, maybe a tap transformer to have different AC voltages, and a signal generator maybe for testing protection. In addition, the green boxes, you may also need a DC source, a drivetrain, if it's a synchronous generator connected to the inverter, or you may have auxiliaries necessary. So now I would like to introduce an example of our laboratory. So we have a laboratory called SysTech. It's a test center for smart grids and electromobility. We have set up this in the years 2009, 2010, and since then we have tested a lot of central inverters up to 2 megawatt, and also combustion engines in the range of 300, 500 kilowatt for biogas. And so we have an AC grid simulator of 1 MVA, a DC source of 3 megawatt, and a tap transformer to adjust the AC voltage. And we also do have ohmic, inductive, and capacitive loads, which can be, which have increments. And we have a mobile under voltage test container. Our over voltage right through test equipment is under development. So for outdoor testing, we also have a MVLV test grid and a hybrid system test bench. So for all this, we also are involved in consultancy. So we may help you with giving you advice in how to design a test lab. So as main specific challenges, this is my last slide, I would like to give this point for utility scale PV inverters. So utility PV inverters may have a differing AC voltage from 300 to 690 volts, and also the DC voltage may vary widely. Therefore, AC source and DC source have to be very wide in their operating range. And you may need additional test equipment like isolating transformers. And so at the last point, I think this is important. So for high power ratings, let's say above 100 or 200 kilowatt, grid simulators are not economically feasible, so it's very expensive. So therefore, for this, medium voltage test equipment is the best solution, we think. So thank you for your attention. I would like to answer your questions.
Any questions, please?
Okay, one question from my side. You were mentioning in the new grid code of India short circuit ratio. What did you mean with that?
So it's
so is it a feature or a bug?
I understood it that way, that you also require a certain short circuit ratio where you connect your plant. So it's a ratio of the rated power of the connected equipment in ratio to the connection point.
Like a minimum required short circuit
power,
in relation to the power plant you want to connect, basically.
So this is how I understood.
This is also something we have in the German grid code, or at least in the FGVTR3 you were mentioning.
So now this is addressed in the Indian grid code. Maybe somebody knows better also.
Please take the mic.
The grid impedance. Okay.
The machine parameter circuit ratio point of view. And you are very right that depending on the size of the machine, whether it is going to give that much of fault level or not.
Okay, thank you.